So what we had been looking at is the random experiment. Okay, so what we have been looking at is the random experiment, and we were trying to do this modeling, okay, for this random phenomena. So we understand now what is this omega, f, and p, right? So omega is the sample space. This is the sample space that we have. F is actually the collection of all the events to which you can assign probability to. So we call that sigma algebra. And P is actually the probability, right? So the probability assignment or the probability measure that we construct based on this, right? So every every event in the sigma algebra can be assigned probability, right? But there were certain random experiments which we looked at, and those random experiments were such that handling a sample space and using it subsequently to do further calculations, it's little cumbersome, it's inconvenient. So for example, if the random experiment was tossing a coin, right? If the random experiment was tossing a coin, as simple as that, then the sample space omega is actually heads and tails. So suppose I want to do some further subsequent calculations. I don't have any real numbers to work with, right? I don't have any real numbers to work with. I only have heads and tails. So it becomes really difficult for me to continue my analysis about this random experiment further. Okay, possibly. Another random experiment is tossing, say, n number of coins independently. Correct. So that was another experiment that we have looked at length, right? So the sample space in this case, if I am allowed to abbreviate heads, H for heads and T for tails, then you understand HHH, all H, then one T and all H, and so on and so forth, right? So this was the sample space and so on and so forth. So this sample space obviously has 2 raised to n different elements, right? So working with this sample space to do subsequent analysis might be difficult. So what we really are going to do now is we are going to define something which is called as random variable. Okay, so what am I going to do? I am going to define something which is called as random variable. What will this random variable do? This random variable will map these outcomes from the sample space to real numbers. Okay, so that is what the random variable is going to do. So I can associate a real number with the outcomes. So the outcomes in the sample space I'll map to real numbers. So many a times you would have realized yourself that when you think of a experiment of tossing a coin, many a times you like inherently automatically assign 1 to heads and 0 to tails, right? So you start thinking about ones and zeros rather than heads and tails when you are thinking about these things also. So what you have already done is you have defined a random variable already, okay, and you are working with random variable because you think working with random variable is easier. Okay, so I think many of you would have already done this already. So that is what we are really going to formalize now. Okay, so we will write down the definition of random variable. So a random variable. So though we call it a variable, random variable, it is actually a function. Okay, so we generally denote it by capital X. Okay, capital X, capital Y, capital Z. These are the letters that we reserve for random variable. So a random variable X is a function from omega to r. Okay, is a function from omega to the set of real numbers r. If the set of all omega in omega such that x omega is equal to x belongs to f. That means that for every x in x. Okay, so this for every x in x. Okay. So what we really are saying here, is that what is this particular set? Do you all agree that this actually is inverse image of this particular real number x? So we collect all the points in the sample space. We collect all the points in the sample space which are getting mapped to x. That's the inverse image, right? So I'm collecting all those points in the sample space. And what is it that I really want to do? I want to check that subset of omega. So this particular set is going to be a subset of omega. What I really want is that this subset of omega belongs to this collection F. That means it's an event to which I can assign probability to. And why am I going to do that? Because that's how I'm going to assign probabilities to a random variable also. Okay, that's why I need this particular thing. right? So this particular set is called as inverse image. Okay, so this particular set is called as inverse image of this particular real number x. And the condition that this set is really belongs to F is for probability assignment. Okay, so what is the probability assignment? So probability that random variable x takes value x, okay, is actually the probability of this set omega belonging to omega such that x omega is equal to x. And now this particular set, which is nothing but inverse image of x, is basically what? Basically this particular set that we insisted to be belonging to F. Now that this set belongs to F, according to the theory that we have seen so far, probability is assigned to that particular set already, right? So the probability is already assigned. So that probability is actually the probability that random variable x takes this value x. So is the definition of random variable clear? So this is something very basic, and I think if you understand the set theory, inverse image notation and all that stuff, then this is not really very difficult. Okay, so let us start from a random experiment. Okay, so let us start from that. So 3 fair coins are tossed. Okay, 3 fair coins are tossed. So this is the random experiment that I am doing. I am giving additional information that these coins are tossed independently. Then we all know that there are 8 elements in the sample space. So let me list them down. H, T, H, T, H, T, T, and T, T. Okay. So this F is basically 2 to the power n, right? So we already have seen that this sigma algebra is actually the power set. And we know that probability of each of the elements here is 1 by 8, right? So probability of every sample space, probability of omega is equal to 1 by 8, which is nothing but half into half into half for every omega belonging to omega. I hope you understand. There are a lot of things that have happened here. We have several times looked into this. So this multiplication happens because of independence of events, and because they are fair coins, so the probability of heads and probability of tails both is half, right? So that's why these probabilities are all 1 by 8. So now I define x. Okay, what is it? Now I define a random variable x to be number of heads in 3 tosses. Okay, so I define this to be the random number of tosses in number of heads in 3 tosses. Okay, and I try to represent this pictorially. Okay, so let us try to represent this pictorially. So this is my omega, and this is my set of real numbers. Suppose this is the set of real numbers. The mapping is going to be through x, and let me enlist these elements again. Okay, T, H, 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 T, H, 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 T, then T, T, H, T, H, T, H, T, T, and T. Right? These are the 8 elements that are sitting here. And suppose I have 0, 1, 2, 3. These are the real numbers coming here. Then what is the mapping? The mapping is that this H, H, H goes to 3. Then what is the other mapping? There are 2 heads in all these 3 guys. So all these 3 guys go to 2. Right? So that is the mapping. Then what is going to happen? Then what is going to happen? You have collection of sample points with one head only. So that is going to go here. That is the mapping that I'm going to have. And finally, you have TTT, which is going to go to 0, right? So this is how the mapping is going to happen. And in this particular mapping, what do? We do the following, right? So for example, if you take x is equal to 1, x belonging to R, if you take x is equal to 1, then what is inverse image of 1? Inverse image of 1 is set of all omega in omega such that x of omega is equal to 1. So what is this? So this set inverse image of 1 is basically, you see, only the 3 guys in highlighted in pink, which have only one head, right? So you have T, T, H, T, H, T, and H, T, T, right? So this is what you have. So how do I assign probability that random variable x takes value 1? This is same as probability of omega in omega such that x omega is equal to 1, or in other words, I am looking at the inverse image of 1. That is the probability. And what is the probability? So we already know that this set belongs to F. That is the definition, right? So first we have to check whether every such inverse image belongs to F or not. So this set belongs to F. So what is the probability? Because it belongs to F, you know the probability is calculated. This probability is 3 by 8. Similarly, you can check X inverse 2. So this set will be H, H, T, H, T, H, and T, H, H. Correct? So this set also belongs to F. You can check X inverse 0. So what is X inverse 0? It is T, T, T. You can check X inverse 3. What is this? This is H, H, H. Right? So all these guys, they belong to F. Right? And now you see the carefully definition of this random variable. It says that for every real number x, this should happen. So what is x inverse of 3.7? What is x inverse of 3.7?
Five.
Huh? This is an empty set. Okay, this is an empty set. Correct. What is x inverse of minus 0.6? What is x inverse of minus 0.6?
5.
This is also 5. So these also belong to F. So except for real numbers 0, 1, 2, 3, all other inverse images are going to be the empty sets. Does empty set belong to F? Yes, empty set belongs to F because we already have said that in this particular case, F is actually equal to 2 power omega, right? Because F is equal to 2 power omega, this is going to happen. So that's why this particular function X is a random variable, correct? So that's why X is a random variable. I think somebody's mic is on. Can you please mute? I cannot figure out. Somebody's mic is on. Please mute. There's a lot of noise coming. So X is a random variable. And how is the probability assignment happening? Probability assignment is happening by inverse image. So what is the probability of X is equal to 2? Probability of X is equal to 2 is also 3 by n. What is probability of X is equal to 0? It is 1 by n. And what is the probability of X is equal to 3? It is also 1 by n. And what is probability of X is equal to 3.7? That probability is basically probability of empty set, right? Probability of empty set is 0. So that is also already known. Minus 0.6, this probability is also 0. So that is how the probability assignment is happening, and that is how you start working with random variables. Okay, so this is one simple example of a random variable. So I hope what we have done here is clear. How do we come up with the definition of random variable? How will you check this is a random variable or not? The concept of inverse image, and through inverse images, how do we do this? I hope this is clear to all of you, right? So this is the random variable. So the range of random variable. So what is the range of random variable? So the range of random variable is basically that set. So the set of all x in R for which probability of x is equal to small x is greater than 0. Okay. So that is what we are going to look at right now. So here in the previous example, I will denote range of x to be this. So the range is 0, 1, 2, 3. Okay. So this definition I will modify slightly. Okay. So this definition I will modify slightly little later. Okay. I will tell you that. Modify slightly. I will do that, and we will see what it means. Okay. So the random variable x has this range in the previous example, right? In the previous. So a random variable. So I will write down the definition. A random variable is called as discrete random variable. A random variable is called as discrete random variable. If range of x is finite or countably infinite. Okay. So countably finite. To be more precise, I'll just write down countably finite, meaning that it's a countable finite set or it's a countably infinite set. Okay, so that is what we call range of a random variable. And there is another thing that you can define right away looking at what we have done. So you can define a function. Okay, so a real valued function fx is equal to probability that x is actually equal to x is called as probability mass function, is called as probability mass function. Okay, so probability mass function PMF is for a discrete random variable. Okay, of discrete random variable x. Okay, so what is the probability mass function that we just have seen? So the probability mass function that we have seen is basically f of x is equal to 1 by 8 for x is equal to 0, is equal to 3 by 8 for x is equal to 1, is equal to 3 by 8 for x is equal to 2, is equal to 1 by 8 for x is equal to 3, and is equal to 0 otherwise. Otherwise meaning for all other values of x, it is actually equal to 0. Otherwise meaning for all other values of x. Okay, so this is how the function fx really looks like, right? So it's a rule, it's a function, and it is called discrete probability mass function. Why it is called discrete probability mass function? Because it is coming out from the probability assignment to the random variable, right? So it is giving. So there are several ways to represent. So people use graphical notation also, so no big deal. So here you have 1 by 8, then this is 3 by 8 value, then this is also 3 by 8 value, so this is 1 by 8, right? So this height is 1 by 8, this height is 3 by 8, and these are the only jumps there, right? So this is kind of graphical representation. So this is kind of graphical representation of fx, and you can have a tabular representation of fx also. So I think this is something that you might have seen in your 12th standard possibly, x fx, and 0 1 2 3, and this is 1 by 8 3 by 8 3 by 8 and 1 by 8, correct? So this is how you can do tabular representation. Okay, so PMFs can be represented by several ways. A formula which is given to you with the range of the random variable. Okay, so that's the formula. Or you can have graphical representation, or you can have tabular representation. Okay, so let us quickly see few examples of this particular discrete random variable, so to speak. Okay, so I'll take first example, which is a very famous distribution, Bernoulli distribution. Okay, so what is the experiment? Experiment is tossing a coin. Okay, this is something that is very important, tossing a coin. Okay, then what is the sample space? My sample space is h and t, and I have probability of h is equal to p, probability of tails is equal to obviously 1 minus p then. Then I define x to be a random variable. Okay, so many a times now I'll just put r dot v to mean a random variable, right? That's the abbreviation that I'll make. So what is this random variable? I say x of head, okay, is actually equal to 1, and x of tail is actually equal to 0. Okay, xt is equal to 0. Then what is probability of x is equal to 0? It is set of all omega in omega such that x of omega is equal to 0. Correct? That's what it is. So what is this set? So this set is basically t. So probability of 0 is probability of t, which is equal to 1 minus p. And similarly, what will be the probability of x is equal to 1? It will be equal to p. So what is the PMF? So the PMF is fx is equal to p for x is equal to 1, is equal to 1 minus p for x is equal to 0, is equal to 0 otherwise. That's the Bernoulli PM. Okay, that's the Bernoulli PM, probability mass function. And what do I say? I say x follows Bernoulli distribution. F follows Bernoulli PMF with
Sir,
parameter. Okay, yes.
sorry to interrupt, but I'm not able to see your screen.
Sagar, actually, you log out and log in again. If you join later and not using app, then there is a problem with the screen. Okay, you cannot see it. So log out and log in again, and you will see. So this is a Bernoulli random variable, and X follows Bernoulli with probability P. Okay, so P is called as probability of success sometimes. Okay, P is called as probability of success sometimes in this Bernoulli trial. So you have a Bernoulli trial. So tossing a coin is actually called as Bernoulli trial, right? This is something that we have already seen. And from that Bernoulli trial, you construct your first random variable, Bernoulli random variable, and this parameter P is something that completely defines, okay, that completely defines this particular random variable. Once you know what is this P, then you know everything about this random variable. Okay, so that's why this parameter is very important. So X is a Bernoulli random variable with parameter. Okay, moving further, we define another random variable, which is binomial random variable. So again, we start with the experiment. So what is the experiment? N independent Bernoulli trials. Okay, N independent Bernoulli trials. So I'll put a P here to indicate that the probability of success in each Bernoulli trial is P are performed. Okay, so this is the experiment. And now what do? We define X. So how do we define X to be the number of successes? Okay, number of successes in these N trials. So this we already have seen, correct? So here I forgot to tell what is the range of this random variable. Range of this random variable is 0, 1. So similarly, now you can see the range of this random variable is 0, 1, 2, because these are the only values, discrete integer values, at which you will have a positive probability assignment. At all other real numbers, the probability assignment for this random variable will be equal to 0. And why? You can see very easily, you can do the inverse image mapping. So I think it is not required. Or do you want me to see? So 1 I will do. Probability X is equal to 1. How do we do this? So this is probability set of all omega in omega such that X of omega is equal to 1. So you have to look at the omega. So typically, how does the omega look like? Omega is those 1, 0, 1, 0 sequences, right? That is what this omega is, or success, failure, based on whatever notation you are using. And now you have to count the number of successes, and the number of successes should be equal to 1. So what are the type of elements that are present here? So you have only one success. So you have success and all other n minus 1 places failure. So failure, success, failure, failure, so on and so forth, failure, 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 success, right? So how many elements are there in this particular set? There are n elements. And what is the probability? The probability is n times 1. So the probability is that n choose 1, and so probability of this set. So this probability is n choose 1, then probability of success into 1 minus probability of how many failures? N minus 1 failures, right? So that is the probability that we have, n into p into 1 minus p to the power n minus 1. That's the probability. So you see, the positive probability assignment is only going to happen for the integer values 0, 1, 2 up to n. At all other real numbers, this probability assignment is going to be 0. So we now define PMF. So how does the PMF looks like? So this is the probability assignment. Probability X is equal to small x, right? And how does the PMF looks like? PMF looks like this. This is equal to n choose x, p raised to x, 1 minus p to the power n minus x, for x taking values 0, 1, 2 up to n, and this is 0 otherwise, right? That's how this looks like. And we call this random variable x, which follows binomial density, binomial, with two parameters n and p. So once you know what is n and what is p, then you know everything about this random variable. So what is n here? N here is number of independent trials, right? So what is n here? N represents number of independent trials. Independent Bernoulli trials, correct? That's what this N represents. And what does P represent? P represents probability of success, correct? P represents probability of success of those independent trials. So this is called a binomial random variable. We'll look at one more example of the random variable before we go further. Okay, so this particular random variable is called as geometric random variable. Okay, so what is the experiment that I'm going to do? The experiment that I'm going to perform is actually perform independent Bernoulli P trials until the first success. Okay, so understand this experiment carefully. What we are going to do, we are going to perform the Bernoulli trials independently until you encounter the first success. So in terms of heads and tails, if you think heads is a success, then you will keep on tossing the coin independently. So that is understood. So you'll keep on tossing the coin until you see the first head, right? So what is the sample space here? The sample space here obviously is you can get success at the first toss, or failure and then success, or FFS, or FFFS, and so on and so forth. So you have countably infinite outcomes in the sample space. And we already have seen even to this how to do the probability assignment. So you know when you do the probability assignment, probability is P here. Probability is 1 minus P into P here. What is the probability? 1 minus P square into P. 1 minus P cube into P, that is the probability, right? So these are the probabilities for this singleton sets. We have already seen this, right? So I define random variable X in this particular case. So what is the random variable X? The number of failures, before the first success. So can you tell me what is the range of this random variable? What is the range of this random variable?
0.
So 0, 1, 2, 3, and so on and so forth. So looking at the range, you can see that this is a discrete random variable, right? Looking at the range, you can see that this is a discrete random variable. Another thing that I want you to see here is that how automatically you were able to say what is the range of this random variable without even explicitly saying what are the inverse images of every real number and how is the probability assignment happening, where it is happening to be positive, where it is happening to be negative. You see, you are automatically doing it. You are so easily doing it. So all these calculations about inverse images and everything is happening probably implicitly in your mind. Okay, you are not even registering it. You are just telling me range is this. So this is something that is very important. So see how nicely this inverse image of us of an element and all these ideas so nicely embedded in your mind, okay, without even realizing that you know these concepts, and you are using them to come up to this particular Rx and so on and so forth. Okay, so that's why it is very important to explicitly write them down and realize that you know these things. Okay, that's why that definition at the beginning of the class is given. So this is the random variable, and now fx, the PMF. What is the PMF? So you can see PMF is this for x is equal to 0, 1, 2, and so on and so forth, and is equal to 0 otherwise, right? That's the PMF. And we say x follows geometric. Okay. So we say X follows geometric P. P is the parameter probability of success. So something interesting has happened here. Something interesting, and I will do the generalization. But you see, three examples I have given. The first example I gave was a Bernoulli trial, and in the Bernoulli trial, you just performed one Bernoulli trial and you recorded heads or tails, success or failure, and then you defined the random variable, which was Bernoulli. Then in binomial, what did you do? Binomial, you said you will do n independent Bernoulli trials. Okay, you fixed the number of trials. So that becomes one of the parameters in Bernoulli. You fix the number of trials. And after you fix the number of trials, you count how many successes are there in those number of trials. distributions, right? So you fix n and then you count how many number of successes. That is the random variable, which is binomial random variable. The name binomial comes because the way you prove that it is a PMF, you see the binomial expansion is going to be used. And the third thing is the geometric random variable. And what is this geometric random variable really doing? You are now fixing the number of successes, so to speak. You are saying that you are interested in only one success. And what you are saying, you want to see how many number of independent Bernoulli trials are required to get that first success, right? So here you had n independent Bernoulli trials and you are counting how many number of successes you have. Here you want only one success and you are counting how many independent Bernoulli trials are required to get that first success. So there is nothing special about one success. I can fix number of successes to be equal to alpha, let us say, and say 10. And how many independent Bernoulli trials I will need to get those 10 successes. Okay, so that distribution will be called as negative binomial distribution. So we'll talk about that distribution little later, but this is what is really happening. So from a Bernoulli trial, you go these two ways and you build two very interesting distributions, right? So this is like your one attempt. This is your one attempt at solving MCQ type of problem, right? So one attempt at solving MCQ, you don't know the answer. So probability of getting correct answer by randomly picking it is P, right? Then what do? You do you fix n trials, right? And how many times you get the correct answer? That's what you are doing. And here something you want correct answer and you keep on trying until you get the correct answer, right? तुक्का लगाते बैठोगे जब तक करेक्ट आंसर नहीं मिलता है तो करेक्ट आंसर कब मिलेगा that is what you are finding out how many times you have to attempt until you get the correct answer, right? So for you these distributions are really important in an online era. You have to understand these probabilities, right? If you want to solve papers you have to understand these things, right, nowadays. So these are important distributions for you. And the generalization of this geometric, which is nothing but negative binomial, right? So these are important discrete random variables. We'll continue with these discrete random variables, but before we go any further, let us try to understand this probability mass function even more closely. Okay, so understanding PMF more closely. Okay, understanding this probability mass function PMF. Okay, so let us see what this PMF is really doing. So omega FP, so this is something like हम लोग का you have this thing, no? Omega कोई लोग एग्जाम का पेपर लिखने से पहले या कुछ शुरू होने से पहले ऐसे श्री या ओम ऐसे कुछ लिखते हैं, नहीं? People have this habit of writing these things, right? So in the probability class, we'll always write omega FP. It is understood. तो ओमेगा एफपी बोले तो तुमको पता होना चाहिए कि कोई एक रैंडम एक्सपेरिमेंट किया, उसका ओमेगा निकला, एफ निकला, पी निकला, राइट? सो इट इज लाइक माय ओम और श्री. ओके, सो एवरी टाइम आई स्टार्ट आई विल राइट ओमेगा एफपी. ओके, सो दैट ओमेगा एफपी is written. So every time I'll not say what is omega fp. Then I define a random variable x. Okay, random variable x. So this is defined on omega, random variable on omega I have already defined. So let Rx, the range of random variable, range of x, be discrete. Okay, be discrete. So it really means that it is finite and countable or infinite and countable. So this is basically a discrete random variable. Okay, so I write down this x as x1, x2, and so on so forth. Okay, because it's a countable set, I will be able to enumerate it and I will be able to list all the elements in the range. Okay, so that is my, so I'm basically looking at this. Then what happens to this? Can you tell me summation fxi for every xi belonging to range? What will this summation be equal to? What will be this summation equal to?
1.
So this summation is actually equal to 1. Yeah, you have guessed it right. This summation is actually equal to 1. And why is this summation 1? Let us closely observe what is really happening, right? So this by definition is probability x is equal to xi. That's the way you assign probabilities. That's the way you define probability mass function. This further is nothing but set of all x in Rx set of probability of all omega in omega such that x omega is equal to x psi. Now, why this sum is equal to 1? I want you to tell me why this sum is actually equal to 1. So this is by definition of this is coming by definition of PMF, right? This is coming by probability assignment to random variable, right? Probability assignment to a random variable, right? So this is something by definition. But now this is equal to 1. Why this is equal to 1, you will tell me. You have given correct answer. I want to know why.
So, if you assume it to be not equal to 1, then there will be some probabilities to be accounted for so that the total sum becomes 1.
So this
But-
can be set from the definition of sigma algebra.
Correct. I want that part. So what you said, that is not a possibility, right? I want to understand it from sigma algebra. How do you do that? Can you tell me?
From the rules that we defined, like the probability of union is equal to the sum of probabilities, and that
Correct.
the
So
probability of the complete.
Correct. Probability of unions is sum of probabilities. That is third axiom. You are
Yes, sir.
Anurag, right? Anurag.
Yes, sir.
Yeah. So probability of union is sum of probabilities, but that is true when? When is that true?
AI is when the outcomes are mutually disjoint.
Correct.
When the events are
when the
mutually
events are mutually disjoint, when the events are mutually disjoint, then sum of probability of union is sum of probabilities. You're absolutely right. The third axiom in the probability, and you'll use the first axiom in the probability that probability of omega is equal to 1, right? So these two axioms.
Yes,
So here, what union you are looking at and why that union is disjoint? Can you tell me? So basically what you are looking at union of all omegas in omega such that x omega is equal to x psi. That's what you are looking at. And you
Yes,
are
sir.
taking union over x psi in Rx, right? So this is what you are looking at. This you claim is disjoint union. That is first claim. And you say that this is equal to omega, entire omega. That's what you say.
Yes.
Anurag, these are the two claims. So first tell me why this union is a disjoint union. First of all, do you all agree that the union has to be equal to omega? I think that is trivial. There is no problem about it. The problem is about it being disjoint. So why is it disjoint?
We can consider the inverse.
relationship.
Sorry.
It is by definition of random variable, right?
What is the definition of the random variable?
I mean,
So we use a function to get from
Correct.
omega to x.
Yes, sir.
So that
Correct.
means by definition it has to only have one output.
Correct. So what a function is allowed to do, so in this set theoretic notation, what a function here is allowed to do is the function can be 1-1 relation or many to one relation, but it cannot be one to many. Correct. If it is one to many, then it's not a function, and that one to many or many to many will give rise to some intersection between these two events, right? You think about it. So what you really are saying is that one omega can map to two different xi's. Okay, is that possible? That is not possible under the definition of function. So the function will allow you to have only one-to-one relation or many-to-one relation, right? So that will guarantee that this union is actually a disjoint union. And that is something that is really very important. I want you to understand. Okay, that is how it is really happening. So now pictorially, if you can imagine, there are all these real numbers sitting here. There is this omega sitting here. And what is this function x, the random variable x, really doing? You look at the inverse images and the random variable is inducing a partition of omega through the inverse images. Can you see that partition of omega through the inverse images? And that partition you take each block in that partition. Each block in that partition is one particular event which corresponds to probability x is equal to small xi. Correct? Do you understand now pictorially? Is it perfectly clear what is really happening? What is the random variable doing? So this is something that you already know. We are just explicitly writing it down. Okay. So this is something that is really very important. So this understanding of random variable tells us that if you add all the probabilities in a probability mass function, the sum has to be equal to 0. Okay. So that is, sorry, sum has to be equal to 1. So that is something that is really very important. Okay. So what have we done so far? So far what we have done. So far what we have done. We started with a random experiment. Right? We started with R. Then the random experiment. Then we went to this omega fp. Right? Then we defined the random variable x. And then from the random variable x, we defined PMF, right? So far, this is the journey that we have taken. Can we trace this journey backwards? Okay, so the question that we want to ask is, can we go backwards? That means that I start with a PMF. Okay, so for that, I first need to understand what is a PMF, right? So I will enlist the properties of PMF first, and we will see we can take this backwards also. So far, this is what we have. Okay, so now let us look at the properties of PMF, important properties of PMF. Okay, so the first property is that fx is greater than or equal to 0 for every x in. So this is obvious because the way we defined PMF, PMF is basically the probability, right? So it has to be greater than or equal to 0. The second part that we define x such that f of x is strictly greater than 0 is a countably finite or countably infinite set. Correct. So what I'm really doing, I'm saying that the range of the random variable should be countably finite. So I will be able to enumerate all the elements in this range like this, right? So this is the set that I have. And now you see, in order to define range, I have slightly modified the definition. When I said the range, I will modify the definition. I had said, right, will modify slightly. So what is the modification that I have done? The modification that I have done is I'm saying fx is greater than 0. Okay, so this is the place where I have modified the definition. And what is the third condition? The third property that I have is that summation f of xi, summation taken over all xi in this Rx. Okay, I will call this set Rx maybe. So this is actually equal to 1. This is what I have done. So these are the three properties of PMF. And in fact, these three properties will call defining properties of PMF. Okay, so what are we going to say? We are going to say that any function which satisfies these three properties, will call it a probability mass function. Okay, so any function f which satisfies these three properties, what is this function called as? Is called as discrete, is called as probability mass function. Okay, probability mass function. It is often abbreviated as PMF, or it is called as discrete density. Okay, it is called as discrete density, but I will say you should use this with caution. Okay, if you are going to get confused between a probability density function PDF and a discrete density, I'll say you just forget this. Okay, later on we'll call something. We'll do something. Okay, so discrete density, if you think it is going to confuse you, you may just forget and just remember this as probability mass function. Okay, so any function f which satisfies these three properties, we will call a probability mass function. Okay, so let us see few examples for probability mass function. So let us see few examples. What are they? So the first example is of uniform PMF. Okay, so we'll call uniform PMF. So I'll define the function f of x to be equal to 1 by s for x belonging to x1, x2 up to xs, okay, and is equal to 0 otherwise. Then is this a probability mass function? Is it a PMF? So how do you do? How do you check? You check by the three defining properties. So what is the first property? The first property is that fx should be greater than equal to 0 for every x in R. Is fx greater than equal to 0? Yes, it is greater than equal to 0 for every real number. The place where it is strictly greater than 0, you collect all those real numbers. That set should be countably finite or countably infinite. In this particular set, the set is actually finite. What is that set? That set is x1, x2 up to xs. And what is the third property? Summation of fxi, xi belonging to that rx should be equal to 1. So clearly the summation is actually equal to 1. So this particular function actually satisfies all the conditions to be a discrete density or a probability mass function. So this function is a probability mass function. Have we encountered this already? We have encountered this already in case of Bernoulli trial when the outputs were only two, x1 and x2, which we called 0 or 1 or heads and tails. And what happened? The coin was fair, so that will be equal to half, or rolling a fair die. In that particular case also you will end up with a uniform probability mass function. Okay, so this is a mass function, uniform PMF. Okay, what is another example? Another example is something which I will write down, negative binomial PMF. Okay, negative binomial PMF. What is it going to do? For an integer alpha belonging to the set. Okay, so maybe I'll just write down for alpha belonging to n. So it is a natural number and p belonging to any real number 0 and 1. I define fx to be equal to p to the power alpha. Alpha plus x minus 1, choose x. 1 minus p to the power x. X is taking values between 0, 1, 2 and so on, and is equal to 0 otherwise. Okay, so this is my definition. This is my definition of probability mass function. So will this be a probability mass function? So you can check that this is a probability mass function, right? The range here is countably infinite set, still discrete. And for the conditions that I have given here, this is a probability mass function. If you take alpha to be equal to 1, have you already seen this particular case? If you take alpha is equal to 1, have you seen this particular case of this? What happens for alpha? Alpha is equal to 1. Negative binomial becomes geometric PDF, geometric density, geometric probability mass function. Can you check that? If you have alpha is equal to 1, this is geometric, right? Can you see this? So this is actually generalization of geometric. And what is the generalization? Generalization being you will keep on tossing the coin, or you will keep on performing the independent Bernoulli trials until you get alpha, number of successes. So this is like number of successes. Okay, these are the number of successes, and this P is actually probability of success in the Bernoulli trials. Okay. So this is not easy to see immediately. So I will say you take some time. You can use this as your homework, and you can prove that this is actually a PMF. Okay. How to relate this PMF with this interpretation that I am trying to give? That is also non-trivial. You take some time to understand if that really is going to happen. Okay, so that is something that I hope you will be able to do as homework. If you cannot do it, we will try to do this once again. Okay, so this is a PMF which is called as negative binomial PMF. Okay, then I'll give some special examples of random variable. Okay, special examples.
Sir?
Yes.
Sir, in that negative binomial
distribution, x is the number of failures, right?
X is the number of failures. That's right.
Okay.
So X is number of failures, and what is the number of successes? Number of successes is alpha, and you keep on trying until you get first alpha successes, right? So like your first outcome of this experiment is SSS alpha number of times. Then you may have to do alpha plus 1 number of trials where one failure happens and alpha successes happen. So the last element always has to be a success, right? So you have alpha minus 1 places, and in those alpha minus 1 places, you have to arrange those many number of failures. So the number of trials you will do is alpha plus X, right? So that alpha plus X minus 1, choose X comes from there, and you just assign probabilities. Those are p raised to alpha and 1 minus p raised to X, right? So I will urge you to write this down very nicely, okay? That is something that I would like to do. And only in a couple of minutes, I want to give two examples of special random variables before we close today. So the first example of the random variable is constant random variable. Okay. So what is this constant random variable doing? I define, so I have omega, f, p, and so on and so forth. I define x to be a function from omega to r, such that x of omega is equal to some constant for every omega in omega, for some constant c. Correct? So every element omega is going to this constant, right? So what is the probability? Probability x is equal to c is 1, and probability x not equal to c is 0, right? That's how the random variable behave. And how does the PMF look like? So suppose this is the number c, this is the height 1, right? So this is the PMF, right? Another important special random variable is called as indicator random variable. Okay. So what does indicator random variable do? So this is indicator random variable. So let a set A belonging to F. Okay, so you have omega FP already done. Like I have said, you already have omega FP, and you consider a set A belonging to F, and you define this particular random variable. I write it chi A as a function from omega to r. Okay, so what is this chi A function doing? Characteristic function. Okay, so this is a indicator random variable. What is it doing? So it is a function from omega to r, and you say chi A omega is equal to 1 for every omega in A, and this is equal to 0 for every omega not in A. Okay, or you can say every omega belonging to A component. Okay, so what is happening? What is happening? You know, whenever omega is in A, you will have probability equal to 1. Otherwise, the probability will be equal to 0. So probability of A will be actually the chi A omega, right? So it is telling you, it is indicating whether the event A has occurred or not, right? So the PMF here will be Bernoulli. If you can see, the PMF here will be Bernoulli, and what are the two outcomes? The two outcomes are omega and 1. Excuse me. Two outcomes are 1 and 0, and the probability of success P is basically equal to probability of A, and 1 minus P is probability of A. Correct? So that's how it will be a Bernoulli random variable. Okay. Excuse me. So this is what I wanted to cover today. It's almost time. We'll continue our discussion about random variables in tomorrow's class. Once again, announcement about the exams for those